So we're going to do the proof of Bernoulli's equation. Which is actually dependent on equation of continuity. First of all, you should understand Bernoulli's equation is nothing but the outcome of or a basic direct significance of the law of conservation of energy. It is actually the outcome of law of conservation of energy. And it is based on the law of conservation of mass. Which is nothing but the equation of continuity. First, we got to derive the equation of continuity, which is you take a container or a pipe. This is our everyday observation. If you have a pipe through which your liquid is flowing, hose pipe, every day we are seeing in our home, hose pipe. Hose pipe say liquid or fluid, what we call as water, is traveling like this. Now we have liquid entering through this narrow surface, a narrow area, whose surface area A1, and coming out from this surface area A2. Or the vice versa can also happen. It could actually travel from this bigger surface and come out from a smaller surface. Either of this can happen. You must understand that the entire tube is filled with water or liquid. Pura filled up. Now what you are doing, you are connecting it to a motor or a pipe. Somehow the liquid has to enter from one surface, the entering liquid. Okay. And liquid is exiting from this other surface. The amount of mass of the liquid that enters, which is green color and pink color you are seeing, this is the amount of mass that has entered in 1 second or same time. It need not be 1 second. Delta t time में कितना enter हुआ उतना ही तो बाहर आएगा. पूरा तो बाहर आ जाएगा ना. Some liquid can't stay inside, no. So to understand that mass is conserved. M1 entry जो होगा, M2 जो बाहर आएगा should and must be same. M1 should be equal to M2. What is M mass means? We know in terms of density, it is defined as mass per volume. So can I write this M1 equal to M2 in terms of the parameters of the pipe or the container? How do we understand? ये जो mass है from here to here M1 enter हुआ, ये जो बाहर आया M2 is the same, one and the same. So how do we understand that? It is equal to density of the liquid into volume V1 is equal to density of the liquid into volume V2. Now what am I saying? Mass
so, over
and
your density will be same, but volume will be different.
Volume will be different. You can very clearly see these volumes are different.
Yeah.
The area is different.
Okay.
Is it or not? Now, what we are talking about is the rate of entry of mass dm by dt on this end is the same as dm2 by dt on the other end. So we are differentiating this equation on both sides with time. So whatever amount of mass entered the tube on the one end is the amount of mass leaving out of the tube on the other end in the same time delta t. We can as well do it without in 1 second also. We are doing it for t seconds. Then what would we get? Obviously, density is cancelling. What is volume? Area into, you can very clearly see here, the fluid has traveled a distance L1 here, entry, and it has come out traveling a distance L2. They are not same. Is it or not? So A1 area, L1 length. Here A2 area, L2 length. We have to differentiate on both sides. Is the area changing is or what? No. What is changing on both sides? Length is what is differentiable. Is it or not? So dl by dt is that which is differentiable. What is the meaning of dl by dt on this side? dl1 by dt means velocity of the fluid. Is it or not? It's basically the velocity of influx of the fluid. So we can call that as A1 V1 is equal to A2 V2. Did you understand this? This is equation of continuity.
So wait, so how did you get L over here?
See here, you observe this. What is volume defined as? Volume is equal to area into length, right? For any cylindrical system or any system, any
Okay.
type of a geometrical shape, even cube, cuboid, volume matlab kya hai? Area into length, is it or not? For a cylinder, this is
Yes,
a
sir.
cylindrical shape. Cylinder ka volume,
Yeah.
what is the volume of the cylinder? Pi r
Pi r
square
square h. Yeah.
h. Here L. Pi r square is nothing but
Okay.
pi r1 square here. And here
Yeah.
pi
Okay.
r2 square. Means this is area
Okay.
A1 into L1. That side area A2 into L2. Understood that? Now what does it mean?
Okay. So
So,
so if we differentiate length, we'll get volume.
no, velocity is velocity. dl by dt. What is dl by dt? Length. If you differentiate length, what are you going to get? Velocity, right? Velocity V1. This is velocity, not volume. Velocity. Velocity of
Okay.
if
So area. Okay. So M1, M2 is equal to area into velocity of the first one by area into velocity of the second one, second mass, right?
exactly.
Okay. So okay.
Velocity of influx of the fluid. Influx of fluid. जो entry है, that entry velocity. And what is V2? Velocity efflux. Efflux means coming out. Efflux of the fluid.
Yes, sir. Understood. Okay.
With what velocity it is coming out. You can very clearly see as the areas are different, the length traveled by them will not be same, right? You can very clearly see that. They won't have the same lengths, no? Here since you see here, you can you can clearly see. This length is different and this length is different.
Yes, sir. Yes, sir.
Totally
That
different.
understood.
ये length छोटा है. This length is more. Is it or not? Why this length is more? Because it's narrow area. Narrow area
Yeah,
has
the
a
area
ज्यादा
is
length.
smaller. Yeah. Okay.
So more length it has to travel. There lesser length it will travel. Same thing you will get. Same volume you will get. Isn't it? Isn't this our
Okay.
daily
Yes.
observation?
Sir.
We have a narrow pipe,
Yes.
narrow
Ma'am.
glass, and a wide glass. In the wide glass and narrow glass, you pour the same 1 liter milk and check what happens. The heights are different. No, you can see. Is it everyday's observation? Yes, the same way. So this is called as equation of continuity. This is the basis of Bernoulli starting. Now,
So
again,
Bernoulli was a scientist, right?
yeah, he's a scientist. His name is
He
Bernoulli.
only found the law of continuity, or law of continuity was found by someone else?
Bernoulli's equation के अंदर ही है. This is found by him only.
Okay. Okay. So law of continuity is also known as Bernoulli's equation.
No, it is one of the basic
It is a
requirement for
part of Bernoulli's equation. Okay.
Bernoulli's equation के अंदर है this one. First, we have to understand that one. Then only we can, without equation of continuity, we cannot derive Bernoulli's equation. We cannot even derive. है ना? तो हमें first equation of continuity derive करना पड़ेगा. That's why we derived it. Now what we are doing? Starting of Bernoulli's equation. Let us consider a fluid which is being pushed by our motor. Motor is doing some work externally, or motor is basically doing work to push the fluid from a lesser cross section area into a higher cross section area. Here only now you need to do work. Do you need to do any work? Does the motor need to do any work? If it is the reverse case, why have I taken this diagram in this way? No student asks this question actually. Why this diagram should be like this only? Why should it be reverse? Why should I not take it like this? ऐसा क्यों नहीं लेना है? Why shouldn't I take this way? This will not give us Bernoulli's equation.
Where,
Why?
sir, this one you're telling wherein the influx area is greater than the efflux area.
Influx area is now what? Lesser, no? A1
Yeah, so
is
it
lesser
can't that
than
so it
A2.
can't be opposite.
Ah, that is what. Why shouldn't we take this and like this and solve the Bernoulli's equation? See, I'll tell you why. Because Bernoulli's equation is actually what? What is the base of Bernoulli's equation? What are we trying to prove in Bernoulli's equation? In Bernoulli's equation, our aim is to find out the work done by the external motor. Work done by external motor to push a fluid through a pipe. Now you tell me if this is the situation. ये जो है situation अभी जो है ये दिख रहा है. Here motor does not do any work, no, not required ना. ऐसे ही water liquid will flow easily, no. With gravity it will happily flow. Why does the motor need to push the fluid? Tell me. Here only the pushing has to
So
be done.
you're telling if the area of influx is greater, there'll be no work by the motor because it will automatically push through the area of
Exactly.
efflux
Area of influx is
if it is
lesser.
smaller.
See this side influx. If this is the situation, okay, यहाँ से liquid को push करना है like this.
Okay, okay, understood, sir, understood.
So
Gravity will
that's
push it instead of the motor. Okay.
यहाँ पे उसकी. That's why we don't take it that way. We got to take this way only. Understand? That's the main
Yes,
thing we
sir,
should understand.
understood.
Now, since the pipe is at some height H2, this end of the pipe is at some height H2, and this end of the pipe is at some H1. This is basically every day is happening in our home. Motor is pushing water from the municipal water from the bottom to our overhead tank. This is what it is doing. Yes, this is the height at which your municipal pipe is. This is the height at which your overhead tank is. Yes, in between all the fluid is there. यहाँ पे पूरा है, liquid is already there. Liquid is still. This is the dynamic liquid. Yes. Now, in a delta T time, some liquid has been pushed by the motor. So, in our physics, we should understand that work done by the motor on the fluid or work done by the man on a system is positive. And work done by the object on the motor or work done by somebody, some object on you is negative. This is the sign convention followed in physics. We should know that. Then only.
Can you repeat, like, if the work I do is positive, but if someone does the work on me, it is negative?
On you is negative.
Okay.
Work done by the motor on the fluid. Here in our case, liquid is positive. Is positive. Okay. And work done similarly, reverse, vice versa. By the water is work done. This is motor on the fluid. Water on water. Work done by the water on nobody actually. Work done by the water or work done by the system. This is called as water. What I'm talking in our physics, we call it system. Work done on the system is like positive. Work done by the system is by the water or by the system is negative. That's the basic convention that you should understand. So
I've written the same thing.
No, not the same thing. Work done by the motor on the liquid. Here, work done by the motor. Water, not the motor.
Work done by the motor is positive. Work done on the motor is negative.
Exactly. On the motor by the liquid. Understood? That is what in our understanding is system. We call it system. We don't call motor, liquid, everything. When we are writing, no, what we write is work done by the system is positive. Work done on the system is negative. This is how we write. Okay. So now work done by the motor on this is positive and work done to push it out, ये जो है बाहर आ रहा है, that is negative. Okay. So that is the difference in the work. We are going to apply now work energy theorem. Work energy theorem, basically. What is work energy theorem? Basically, work done. It is the work done is equal to, or work done by the system. Total net work done by the system. System means here motor. Net work done by the system is equal to change in the potential energy plus change in the kinetic energy. This is the work energy theorem. Now you just have to apply that. Here, some force you are applying on this in a delta t time. In a delta t time, from here to here, L1 distance, the liquid has been pushed by the motor. And in the same delta t time, the liquid has moved a distance L2. Okay. So we can very clearly see that. So that is what understood. The same delta t time mein, this liquid has been pushed out. A flux ho gaya, bahar chala gaya. Okay. You can see that very clearly. Of course, this should be more. Obviously, this will be more. No? This delta, this length will be more. This is your L1. This L2 is lesser. You can very clearly see that. Because A2 is more, no? So L2 will be less. Now you are exerting a pressure. The pressure is doing this work. Work means what? What is the formula of work? Force into distance. Yes or no? Yes. You know this. Work is equal to force into distance S. But we neither have force nor can we measure the distance. So that is why in thermodynamics and chemistry, the fluids ke liye a new formula has been derived. Force is defined as pressure into area and distance is L. Yes or no? And we very well know what is area into length. If it is pressure. Pressure into area is force, because pressure is defined that way, no? Pressure is defined as force acting per unit area. So force is defined as pressure into area into distance L. What is A into L? Area into length is that volume existing at that instantaneous volume, है ना? वो capital V, है ना? So P1 pressure we exerted on V1 volume. This is the work done by the motor to push the liquid into it. Is it or not? But that's not the whole thing. This is the work done by pushing. ये जो work done के वजह से some fluid is coming out. No, the mass of some mass of the fluid which you pushed inside, the same mass is coming out. So that what which is coming out, this is the work, total work done. क्या होगा? Net work done is subtraction, ना? Subtraction. So P1 delta V, P1 V1 जो है P1 V1 minus P2 V2. Is it or not? Did you understand that? But
yes, sir.
Volume that is entering is equal to volume that is coming out. Na? That's quite obvious. V1 V2 होता है क्या? V1 is the what is volume V1? That is A1 L1. And what is volume A2 V2? Same thing, A2 L2. But volume of entry is equal to volume of output. जो बाहर आ रहा है.
Yes, sir.
So P1 minus P2 into, I would call that as V only, because both are same. ये भी volume V है, ये भी volume V है. Let us call this as delta V. Same thing. Okay. जो entry fluid है वो is equal to change in the potential energy. What heights they are at? H2 height and H1 height. So M mass of the fluid, G H2 minus H1. Understood that? Plus change in the kinetic energy, half M exit velocity V2 minus entry velocity V1 square. Yes, half m V2 square minus half m V1 square. Understood this? Okay.
So over here, the exit velocity and the entry velocity won't be same.
No, how can it be? That's what is A1 V1 is equal to A2 V2, no? That is what is A1 V1 is equal to A2 V2, right? A1 is less, so V1 is more. A2 is more, so V2 will be less. Is it or not? Will it be the same?
Okay,
No.
sir.
A1 is lesser than A2. So V1 will be very, very large compared to V2. Is it or not? That's what is A1 V1 is equal to A2 V2. है ना? Yes. Okay, इसके बाद.
Okay, sir.
Understood this? Okay. अभी ये
Yes, sir.
प्रेशर डिफरेंस जो बोल रहे हैं, we can write this pressure difference from the earlier known equation rho g into h2 minus h1, change in the heights into delta v1 is equal to mass. What is mass? Mass of the fluid means density into volume, which is delta v, है ना? Mass of the small mass of the fluid that's entering is equal to same.
Yes, sir.
Yeah? So can I write that here? So mass के जगह पे I will write that as rho delta v. Volume है ये. We don't get confused. This is not velocity. Volume.
So the delta V on the both the sides are equal, right?
Yeah, volume is the same ना. जो volume enter होगा
Okay,
वही
that's
volume
what I
बाहर
asked.
आएगा ना. Amount of volume of fluid that enters is the same as volume of fluid that comes out. Pressure difference is changing. This is small v. Don't get confused with this v and that v. See, that's why I'm
Yes,
writing
sir.
also differently. You see the script I am putting. You can very clearly see that. There is a difference. Can you see the difference?
Yes, sir.
Yeah. So for your understanding, I'm putting this green. See, this is different. This is velocity. This is volume. Now you can see on either side, you can cancel this delta v. You know? Yes. So what are we left with?
Yeah.
Oh,
The density won't get cancelled.
of course, density also. Yes, density. So क्या आएगा यहाँ पे? Density also cancel. So क्या आएगा? G into H2 minus H1 is equal to G into. But we don't like to write this actually this way. Actually, we like to put this as pressure difference, pressure only. If you put it this way also we can write, but it doesn't make the actual Bernoulli's equation which we actually require. So what we're going to do is, we're not going to cancel these densities. We're going to put it in pressure difference only. As a pressure difference में छोड़ दो. Because we want the Bernoulli's equation in terms of pressure भी चाहिए ना. We want pressure also. So leave that as P1 minus P2 into delta V and cancel only delta V on both sides. So leave it like that. So here P1 minus, we're talking something which I can't understand. Rho G delta H plus half rho into P2 square minus P1.
Right, delta V, no, sir.
Delta V cancel कर दिया ना मैंने.
No, we can write delta V square for V2
No,
minus
no,
V1.
no, no. We can't write. No, it is V2 square minus V1 square. We can't write like that. How can we write like that? Cannot write. So that is why we are going to take all ones on one side. See what I'm going to do in next step. Pressure P1. This is H1 and a minus H1. Can I take it this side? So that will become plus rho G H1. है ना? H1 को इस तरफ लेके आ गए. All plus minus one terms को इस तरफ लेके आ जाओ. Plus here also you have a minus. So what will you get? Rho by 2 P1 square. This side what? This P2 take it that side. P2 plus rho G H2 plus rho by 2 P2 square. Understood this? This is Bernoulli's
Yes, sir.
equation. This is what is Bernoulli's equation and what is each term having a meaning. First term is called as pressure head, which is pressure. Second term is called as potential head, which is potential energy. Third term is called kinetic head, which is the kinetic energy. So in general, we're going to write this as pressure plus rho GH plus half rho by 2 V square is a constant. This is called as Bernoulli's equation, most general form. When Bernoulli's equation,
Okay.
most general form is this. Did you understand that? The first term is called pressure head. Pressure head. Head why we call? Because it is divided by volume. That is why it's got that name. The first term is called pressure head. This thing. Okay. Pressure dikh raha hai na? This term is called as pressure head. Second term, this one. It's called as potential head. The third term you can see this one is having a name kinetic head. Okay, so the sum of pressure head plus potential head plus kinetic head are a constant. Pressure head meaning what? Pressure energy per unit volume. Potential energy means potential energy per unit volume. It's very clearly seen there. Density में लिखा है. Density means mass per unit volume. है ना? Yes. So mgh by v. This is nothing but mgh by v. Potential head means what? mgh divided by volume. Here, this kinetic head means what? Half mv square. This is velocity. Don't get confused. This is volume. I will better write VUL. Don't get confused. Okay. Right? Pressure head means what? Work done. This is basically work done by volume. This is also called energy density. Another name for this is energy density or work density. There are several names like that. Okay. Understood? This is called as the basic equation of Bernoulli's equation. Whether it is correct or not, how to check, how to verify it. Now, the verification I will tell you. You take the fluid in the container such that it is at same height from the ground. Height difference in years. Same height from the ground. Then what will happen? H1 is equal to H2, no? H1 equal to H2. Then what will happen to this equation? You see, here it will become 0. This term won't exist. Second term won't exist. Then what will you get? Capital P1 minus capital P2 will come out to be that side 0 plus
Kinetic energy.
only kinetic energy. Isn't that obvious? The work done is equal to,
Yeah.
this is only basic equation of work energy theorem. The change in the work done is defined as the change in the kinetic energies. Yes, this is the basic equation of work energy theorem. If you write in terms of mass, you will
Yes,
get
sir.
half mv2 square. This is only what? W equal to kf minus ki, which is work energy theorem, which we know very well. Yes, sir. So this is only Bernoulli's equation, nothing but another way of writing work energy theorem. Is it or not? Yes. But Bernoulli's equation is not valid always. It is valid only when the fluid is having very less viscosity. If the fluid is having a little higher viscosity, Bernoulli's equation will not work. Why? Because as the fluid ka viscosity badega, it will drag the container. It will drag. We have seen in a municipal tap, you can see municipal taps, we keep on cleaning every now and then. Why do we clean? Because they are high viscous fluid is coming through our municipal tap. What is the water that we should get is actually pH 14, but we don't get that. We actually get some other water which is having very high hard water. We're getting hard water means it's having high viscosity. So it is dragging through the tube, and the tube is actually getting corroded. So this way, Bernoulli's equation is valid only if there is no viscosity. Okay, the property of the fluid by which it drags the container and it will try to drag anything, any object around it. It's called viscosity. The fluid ka property hai. It will try to drag the container. So the drag is not there. Then only Bernoulli's equation is valid. Otherwise, it's not valid. There will be some loss of
So it will
energy.
be valid only for a few fluids, right?
Pure, real, ideal fluids. Ideal fluids. It is valid only for
What
ideal.
are ideal fluids? So
Ideal
like
fluids
examples of
means
ideal
low
fluids are.
viscosity, high density. Low
No, so what
viscosity.
are the examples?
Water, pure water, distilled water, H2O. Only H2O or H2SO4, sulfuric acid, or
What about
HCl.
mercury then?
Mercury also, yes. High density, low viscosity. Basically, I told you, high density, low viscosity, very low viscosity. Mercury has low viscosity, zero almost. This mercury ka to viscosity almost zero. Have you ever seen mercury drop sticking onto any container or anything? No, it will never stick. It will never stick because it has no viscosity at all. You cannot. Mercury will always try to form drops. The reason is low viscosity and high surface tension. That's one more reason. One more reason is there in mercury. Because surface tension is one more reason. Three reasons mercury is the best fluid for considering it as ideal fluid. First is high density 13.6, low viscosity, no viscous drag at all, and high surface tension. That's one more reason. These three reasons are responsible for making it as ideal fluid. It will perfectly obey Bernoulli's equation. That's why earlier thermometers used to use the mercury, but nowadays nobody is using, of course, mercury thermometer. It is dangerous. It's a poison, no? Mercury is poison. Even if it one drop goes into our body, we will die. That is the reason. No, but of course, the mercury thermometer, the temperature that it shows is exact point dot value you will get. But the thermometers which we are using nowadays, what are digital thermometers? No, they are semiconductors in which an electronic chip would be there, and that thermometer shows 96.4. It's not exact. It is having 10%, 20% what is it called as error is there. 10 to 20% error will be there. So they are not correct. Even now also doctors use mercury thermometers only. If you go to a doctor, they would not use a digital thermometer. They will still be using their old thermometer only, because that is accurate, exact temperature you will get. Because its expansion is of mercury is based on temperature. Its alpha is alpha, the temperature coefficient of alpha, what we call, is exactly well defined. Right? So this is about Bernoulli's equation. Next, the application of Bernoulli's equation, in which we have two apparatus. One is Torricelli's law or Torricelli's apparatus, and second is Venturi meter. Okay.
We can skip Torricelli, so that I know. We can do
That you
Venturi
know, no?
meter.
That's very simple, no? Very
Yeah,
simple.
Torricelli, I know.
Basically, what in your water bottle, you have a plug. You just have a water bottle में एक छोटा सा hole कर दिया, तो क्या होगा? Water will flow like this. How it will flow? The velocity of efflux of the fluid is equal to root 2 GH, and which is this is height. This height we are worried about, not this height. Generally, freely falling body के लिए also root 2 GH, but this height. This is the height of the object. But here depth of the object from the bottom, from the top of the container is what is the velocity with which it will come out. So Venturi meter is based on Torricelli's law only. Torricelli law पे depend हो रहा है. Venturi meter. It's a construction which is very, very important. We can see this Venturi meter. When this tap cleaning वाले आते हैं ना, जो municipality वाले, you can see in their hand it will be there. When this floods and all come, Venturimeter is the instrument that actually measures the flow of fluid. It basically measures the fluid flow. How do we measure that? There's an instrument like this. Basically, venturimeter looks something like this. Right. So this is how a venturimeter basically is. It is having a U-shaped. This is for inlet of the fluid and this for outlet. ये जो है outlet of the fluid. यहाँ पे small hole will be there. Okay. So this is basically how the construction of a venturimeter is. So liquid tries to enter the venturimeter like this, goes into this narrow part. And then goes out like this. Okay. So these are the streamlines of the streamline flow. Venturimeter also works only if the fluid is streamlined. If it is not streamlined, venturimeter cannot work because Bernoulli's only won't work. Bernoulli's equation only doesn't work for non-streamlined flow. For laminar flow, nothing will work. Only for streamlined flow only. ये streamlined है. That is our approximation. Only then venturimeter works. So these are the lines of flow or laminar lines of flow. Now what happens? There is a manometer. This is a manometer. In which mercury is there, obviously. Mercury liquid is there. As soon as you connect this manometer, what happens is there will be a difference in the heights. Pressure difference will start existing. Why pressure difference is coming? You can very clearly see because of this area here. Because the differential areas, here the area A1 is very high compared to this area A2, which is very, very low. So area difference, area high area. So velocity of the fluid V1 is very, very less compared to the velocity V2. Is it or not? So ये जो V1 is very, very less compared to V2. So यहाँ पे pressure, high pressure to low pressure, no pressure difference will be there. That pressure difference के वजह से what will happen? Liquid will be pushed downwards. So this difference in the heights. What's the difference in the heights? This is the fluid. This is air. Can you see? This is not fluid. Green is the fluid. This is air. You can see this blue thing is air. Because of pressure difference, this is happening. So there will be a height difference. You can very clearly see the difference of heights. ये देखो यहाँ पे height क्या है. And this height. Yes. Now you can see ना ये जो height difference दिख रहा है ना, that is h due to the pressure difference. Now apply the Bernoulli's equation at this point and this narrow point. Here this is capital A, let us take big area. According to your textbook, I'm just telling you, this is smaller area, which is A2 for me, according to me. Yes. So we can very clearly see V2 is very, very larger. No? V2 jo hai, very, very larger. Velocity V2 means don't tell its volume. Okay. इसीलिए मैं script लिख रहा हूँ. V2 is very, very larger than V1 because A2, which is the small a, according to the textbook notation, small a is very, very lesser, smaller than capital A. So what happens? A1 V1 is equal to A2 V2. Now only one small approximation we require. This is not approximation. It is allowed to accept this. That approximation which we need to understand to derive this derivation is before applying Bernoulli's. What is Bernoulli's actually? Bernoulli's equation: pressure head plus potential head plus kinetic head. Is it or not? Yes. So you can see this line. Can you see the straight line? तो ये जो straight यहाँ पे liquid जो है, whatever fluid is there, no, not liquid, liquid or fluid, and यहाँ पे जो है are at same height, ना? Height difference is not there. So potential energy is not there. There is no difference in the potential energy of the fluid at this influx and outflux. That is the only approximation we should take under consideration. Now apply Bernoulli's equation at influx and outflux. What do you get? This pressure at this point is P1 plus, as I told you, there is no height difference. Only kinetic energy will be there. Is it or not? Only kinetic energy, half rho V1 square plus there is no potential energy, so I'm writing 0 is equal to that side what? Some pressure P2 plus half rho V2 square plus there is no height difference. Yes. Yes, you understand that. Now we very well know what is V1, V2. How? V2 we can't measure, no? V2 is immeasurable. We cannot measure the velocity of the fluid inside the narrow pipe. But we know very well that V1 into capital A should be equal to V2 into small a. So what is V2? Which is nothing but capital A by small a. The big area by small area into V1. Yes or no? Okay, इसके बाद. So we can write this as half rho. Instead of V2, we can write that as, this is called multiplication of velocities, velocity multiplier. You know? So P1 plus half rho. Why this happens? Equation of continuity.
Okay, sir.
So we got the V1. हमें चाहिए V1. We got all V1s on one side. Yes, we got to put all these V1s. We take this side and इसको P1 minus P2 लिख दो इसको. P1 high pressure minus low pressure is equal to, इसमें से half rho we can take common from both of them. What are we going to get? A by small a into V1 whole square minus V1 square. Right? So I'm going to take the V1 square common out of this. So V1 square if you take out, what are you left with? Of course, this whole is one bracket.
Half row, sir.
हाँ, ये जो half row है, इसको भी मैं बाहर लिखूंगा. और ये जो अंदर है that is a square, a by capital A by small a whole square minus 1. वही तो बचेगा ना, nothing else will remain.
Yes, sir.
Is equal to P1 minus P2. But we know what is the change in the pressures. We know the derivation is rho GH. Which rho GH? This you should be very, you should know which rho we should take. Density of the liquid or the fluid or the water that is going, that density into G into H. Yes, which H? This height difference. You can see that height difference in the manometer. Okay, that is only the pressure. Pressure exerted. This pressure, यहाँ पे जो pressure है P1, यहाँ पे जो pressure है P2. Here high pressure, here low pressure. That's why high pressure to low pressure. Liquid is being pressed, pulled, pushed. No, liquid will move from high pressure to low pressure. No.
Okay.
Yes or no? So we got that P1 minus P2 is equal to rho of the liquid into G into H difference in the manometer. That's how we measure the pressure difference. Now we want V1. Our aim is to find V1. So put V1 on one side, V1 square if you want to put that side. And all terms that's it. 2 rho liquid GH by this rho is different. Again, I'm telling you that rho is different. This rho is different. This is rho of the liquid. Okay. This is the rho of the medium, we call it. And this rho is different. Into that 1
The
by.
other row is the density of the.
This rho,
The
ये
other
जो
row is
rho
the
क्या है?
density of the.
This rho is the density of the, this rho जो है, I'll write this. Rho M. This is rho M. और ये this rho. Okay. Density of
Okay,
fluid.
the other row M is the density of manometer and the other row is the
Mercury.
density of the ventimeter.
Correct. This is the density of the liquid. And this is the manometer, mercury. That's why M I wrote mercury. Mercury manometer. I'm writing it for you. Now it's clear. Niche, we have this thing. Understood? Now this is square.
Yes.
We would like to write it as a root. So we want V1 alone. So it is root over 2 rho GH rho mgh by rho liquid into, of course, root over 1 by A by square. Understood? This is the
Yes, sir.
velocity equation. Velocity of influx of the liquid through a Venturi meter is given by this. They will generally give in numericals. Capital A is equal to something, capital B is equal to something, they will give. Now small a is equal to something, then we have to solve that. Understood?
Okay, sir.
Based on this, so many numericals are there. IIT concepts I have not still started. All that we have to do. When shall we? When we will do all those?
Sir, when Ishan is back, we'll do. And so, sir, if we are done with this, can we continue the next rest in the next class?
Ah, yes, okay. Finished.
Okay, sir. Thank you. I'm still left with one class, no, sir, out of 10.
I have to count. Yeah, maybe. Let me count.
Yes, sir. Okay.
Okay. Bye bye.